So the final talk, or the final full-length talk of this first half of the session, is going to be given by Mark Nottingham. He's going to be talking about noble gas systematics of soil-like Apollo 16 regolith breccias. So I will set my timer going, and when you're ready, Mark, it's over to you.
Okay, can everyone see those slides?
Yep.
Yep. Excellent. Well, hello, and thanks for this opportunity to talk to you all about some of the work that some colleagues shown here and I have been working on investigating how the noble gases contained within the soil-like Apollo 16 regolith breccias fit into our current understanding of the landing site. There we go. So this work forms part of a broader investigation of these samples. And we sought to kind of constrain the time when they consolidated into rocks, and from that understand kind of what the complete timeline of breccia formation within the Apollo 16 landing site looks like. And then further to that, understanding what they might tell us about the delivery of projectile material to the landing site, and then the mobilization of that material around the landing site. But to start off, I thought it was important to first touch on the ways that noble gases are added, removed, and mobilized around the lunar surface. This is kind of a simplified illustration of the processes that I'll be talking about through the rest of this talk. We have radiogenic sources. These are gases derived from processes such as the decay of potassium-40 into argon-40. They happen in situ within the rock. You have external sources of gases, such as the implantation of gases from the solar wind, or gases that are accelerated back and implanted into a sample by the solar wind. And then finally, we have the cosmogenic gases, which are gases derived from nuclear spallation between target elements into noble gas species. I think it's also important for me to just establish what I mean by certain terminology, and tie that into how that fits in, how this terminology fits in with the gas component types that I previously talked about. So through this talk, I'll be talking a lot about maturity, which I'm saying is a measure of how pronounced space weathering effects are within a sample. We're also discussing antiquity, which is when a breccia was consolidated into a solid rock and became closed to significant additions of exospheric gases. And then finally, we've got the cosmic ray exposure ages, which I imagine more of you are familiar with. But they're the duration of exposure to the cosmic ray flux that's necessary to explain a sample's cosmogenic gas contents, given a specified set of exposure assumptions. So the Apollo 16 landing site, just as a bit of background, is situated on the near side lunar highlands in an area that shows evidence of ejecta that was formed by the Imbrium Basin, which is the Cayley Plains, and the Nectaris Basin forming event, which is represented in the Dakar Formation. And the lander touched down within the Cayley Plains, but samples were collected from both regions. So we're looking at regolith breccias, which are consolidated lithological units of superficial soil, rock, and mineral fragments. And the sample suite from the Apollo 16 landing site yielded a wide array of these types of samples. And it's thought that these samples collectively sample impact processing events from prior to the late heavy bombardment through to the post-bombardment epochs. So that's before 4.2 billion years, all the way through to kind of after 3.8 billion years. So that extensive regolith breccia suite has been broadly grouped by various bits of research into the following groups. We've got the ancient regolith breccias, which consolidated between 3.8 to 3.4 billion years ago. And these formed from very immature regolith, which has been shown to be quite gas poor. We also have the young regolith breccias, which consolidated between 2.5 and 1.7 billion years. And again, they're notably more mature than the ancient breccias, but far less mature than this potential third group. So a third group that's been identified based on textural features, which is the soil-like breccias. But what do I mean by soil-like? Well, soil is defined as the less than 1 millimeter grain size fraction of the regolith, and crucially, it contains components like volcanic glass beads, glass beads, agglutinates, and lithic fragments, which the backscatter SEM image on the left here just points out a few of those components in one of the samples that we measured. A lot of this work was kind of driven by there not being any reported noble gas measurements for these soil-like breccias. So we really wanted to see whether the noble gases would confirm that these are legitimately a different group to the two previous groups. So we visually identified a set of 10 soil-like breccias from a range of sampling sites across the Apollo 16 landing site. And we also selected them for a range of maturities based on their nanophase ion measurements. The images on the left are just some backscatter electron maps of the samples. So we measured each sample on a Thermo Fisher Helix mass spectrometer using laser stepped heating to try and separate those surface situated gases from the crystal bound cosmogenic gases and radiogenic gases. We used cryogenic element separation to allow measurement of each noble gas in isolation, which really just improves the accuracy of our measurements. So what were the results? Well, based on the concentrations of each gas measured, these samples are more comparable to the soils that were collected from the landing site during the mission. The isotopic ratios, which I haven't shown here just to save some time, suggest that each noble gas element, the contents of those can be explained as a mix of implanted solar wind, cosmogenic, and in some cases, perhaps some radiogenic gases. But we do find that the radiogenic gases for most elements aren't a necessary addition to the model. When we compare each element, major isotopes of each element, there are suggestions that we have lost some helium from many of these samples, and in a few cases, possibly some neon. And again, it looked from both the textural analysis and from the argon values of certain samples that they were more consistent with an impact melt sample rather than a regolith breccia. So we then took those concentrations specifically for argon and calculated the antiquity ages based on the parentless 40 argon 36 argon system, adopting the calibration of Joy et al. 2011. I won't go too much into these, but while the uncertainties of these calculations are quite high, they can, or they do still form a rough timeline between the oldest and the youngest samples. And hopefully, as you can see, the calculated antiquity ages
2 minutes, Mark.
Span the range of the young breccia group and into the range of closure ages that have been published for the Apollo 16 soils. On the cosmogenic side of things, we calculated the exposure ages for helium, neon, argon, and xenon. We assume, based on the neon isotopic ratios, that the average shielding depth of each sample resides within 10 grams per square centimetre, which we simplify to 0 grams per square centimetre, so as if they were sat on the very surface of the moon for their entire exposure. We adopt bulk sample chemistry from literature and the theoretical production rate models of Hohenberg et al. 1978, mainly because they answer, they include solar cosmic ray production, so account for a better model of exposure on the surface. These calculations for helium yielded a range of 2 to 5 million years. For neon, 2 to 16 million years. For argon, 30 to 100 million years. And for xenon, 10 to 35 million years. The errors on all of these are approximately 10%. Because of the production rate models used. However, these calculations are strongly affected by things like shielding depth, which is, there's a demonstration of that on the left. You can see you really get divergence between each system with increasing depth. These inconsistencies between the calculated ages may be due to sample degassing, or they could be due to any of these parameters that are listed here. So to try and account for this, we recalculated the exposure ages from literature samples using the same method we used for our own samples. So, because I'm aware time is running out, time has probably run out. How does this all fit together? Well, to recap, the concentrations suggest formation from a mature soil, like those collected at the landing site. The antiquity ages show continuity of breccia formation between the young breccia group and the more modern Apollo 16 soils. And the exposure ages are actually generally higher than any other sample collected from the landing site. So it could possibly mean that there is admixture of regolith materials from older surfaces into these samples in particular. So with that, I think I will leave that summary up for people to read and welcome any questions. Thank you.